Oh my gosh, I'm an electromagnetic wave. Okay, so the goal of this video is to talk about electromagnetic waves, just some of the basics. Give me just a second. All right, and let me get this simulation ready. All right, that's good. Okay, so actually, maybe let's start with the simulation and talk about this electromagnetic wave. So let me share my screen. Let's go this way. All right, and so I'm going to click and this simulation should start. All right, I'm going to swivel it a little bit so you can see. I got to move it slowly. Whoa. All right, that's giving me a little bit of confusing. Hopefully you can see the wave kind of coming out of the screen at you. Let me rotate this back this way. And let's go up a little bit. You might notice what's happening kind of right in this area here. You'll see a red arrow, or kind of a pink arrow or a magenta arrow and a purple arrow oscillating back and forth, going up and down. In this, we've talked about waves already in this class, so maybe if I just get right to it, the yellow is the electric field, and it's going to be a little bit confusing. We're going to call this E. Normally, we would talk in depth about the electric field in an electricity and magnetism course. So if you've already had that course, this probably makes a lot of sense to you. You've probably seen this already. The blue one over here, the blue arrows are the B field. All right, meaning magnetic field. Sorry about that. So the electric field and the magnetic field are oscillating. So again, if you look kind of in this region here at the purple arrow and the pink arrow, the pink arrow is oscillating up and down, or the arrow that was oscillating up and down. Go figure, it just timed out. Let me just do. We saw that. Let me do it this way. There was a pink arrow that oscillated up and down, up and down. And so we see that the electric field was oscillating in the J hat. So at some random X value, we see the electric field is oscillating in the J hat. I'm going to fill in this equation here later. Now, so in this case, this is the Y axis. And then I believe this was the X axis down here. And so this is the Z axis coming out of the page. Now, you should always check a cross product. X goes to Y, goes to Z. You could use your right hand rules to check that. It does. All right. And now where was that purple one? This purple vector right here is oscillating into and out of the page. So we saw that the B field at some position X is going in and out in the K hat here. Just want to make sure that's what I want to do. Yeah. And I will fill in this equation in just a minute. But that's what we're seeing. There's some sort of X dependence. You might also notice there's a time dependence, like any wave. And then we see that's in the J hat. Similarly, the electric field also depended on the time. So the value of the electric field in the J hat direction, up and down, depended on both the position and the time. The magnetic field in a wave depends on both the position and the time, and it oscillates into and out of the page. So just running this one more time so you can see that. Let me clear my annotations here. Whoops. Clear all the drawings, stop this. Let's just run this program again. So this is a pure horizontal view, and I'm just going to rotate it slightly up. Now when I play this, right, you could see the yellow arrows are going up and down. If I rotate it a little bit more, the B fields are going into and out of the page, the magnetic fields. Sometimes you hear me call them B fields. All right, and there's our wave oscillating up and down, up and down. All right, enough of that. That's kind of the concept here of a sinusoidal traveling wave representing an electromagnetic wave. Let's go to the whiteboard. Just like the sinusoidal waves we talked about earlier in the semester in chapter, I don't know what the heck chapter it was. There's a wave number, all right? Well, obviously there's a wavelength, which has units of meters, and a period, which has units of seconds. The wave number, just like before, is 2 pi over the wavelength. That's going to have meters to the -1, inverse meters as units. Angular frequency and frequency, F was 1 over the period, which has units of hertz, which is seconds to the -1. Angular frequency was 2 pi over the period, which has units of radians per second, which is slightly different than hertz, but radians have no units. Wave speed. So here, in general, we've been saying V, but I want to be a little bit careful because we're going to introduce a new term called the index of refraction, lowercase n. I'll explain this in a minute. So we'll either use C or V for wave speed. And it turns out they're related right here. So a vacuum and air is essentially a vacuum as far as light wave is concerned. I think they only differ in like the 4th or 5th spot. We say that the index of refraction of a vacuum is 1. Air is something like 1.00 something. It might have another 0 too. It might be like 0.07. It depends on how much air you have, how much partial vacuum you have, humidity, etc., particles in the air. So it's gonna, but yeah, so air and vacuum for this class basically have an index of refraction of 1. So there's gonna be a wave coming in here. Right, and we're gonna say the speed V in a vacuum, we use the symbol C. That number is, what is it, 2.998 times 10 to the 8th meters per second. That's C, the speed of light in a vacuum. All right, which is essentially the speed of light in air to 4 sig figs. All right, and I just want to make sure I got that number. That the number I put on the back of the book? Yes, that's the number I put on the back. A lot of times you'll see 3.00. That's a good number too. I mean, come on, right? But if we want to have numbers right to 3 sig figs, we'll keep this one to 4. Then we don't have intermediate rounding on that issue. Now, when you go into water, water has an index of 1.33, and depending which book you're reading and which day, sometimes they'll put another 3 on there. So what does this mean? How does the wave speed in water relate to the wave speed in a vacuum? Well, don't get jealous. But I want you to know that C equals NV. Ha ha ha. Okay. So in this case, you could rearrange this and say V equals C over N. The larger your index of refraction, the slower the speed of the wave. So, right, when we say the speed of light is different in air or vacuum and water. Or glass. Glass has an index. There's many types of glass. It usually ranges from about 1.45 up to 1.8. Diamond, what is it, 2.4 or something? We'll get to this in depth later. But for now, I just wanted to introduce the concept of an index of refraction. The index of refraction basically tells us how the speed changes as we go to another medium. So notice what happens. If your light wave is in a vacuum, what's going to happen to the speed? If you enter a medium, so if you don't know what I mean by medium, vacuum is one medium, air is another medium, water is a medium, glass is a medium. It's just the medium through which the wave is traveling. So if you enter a medium with a higher index, the speed decreases. The wavelength is given by this formula. So the wavelength also decreases, right? If n is a big number, if you go into a bigger number, the wavelength is going to shrink. It's still red light. It still looks red, but what's going to happen here? There's going to be some reflection, some transmission, more on that in another video, but the wavelength is going to decrease in size. Now, this is kind of exaggerated a little bit, right? The wavelength should decrease by this factor. That's probably not exactly the right factor, but the idea here is the wavelength shrinks. Okay, so when you enter a higher index medium, the speed goes down, the wavelength decreases, the energy doesn't do anything. And the frequency stays constant. All right. So that's just some facts, and you should have this on lock by the next test. Okay, I know this is just the first lecture before the next test, but you kind of want it. We're going to use this over and over again, so get used to that. All right. These are some basic terms. Let's go over to our equations here. Let's get to a different board. All right. There's going to be some amplitude of the wave times sine of kx minus omega t, and that was in the j hat, I believe. I just want to get my notes right. Yes. Now you could talk about a phase angle. Let's not. Okay. The amplitude of the magnetic field. I guess I'm just making clear. When I say magnetic field, that means the entire sinusoidal wave, all the blue arrows in that wave. When I talk about the magnetic field amplitude, that's just the maximum arrow size of one of the arrows, right? It's the maximum size of an arrow. Geez, I'm tired. It's the maximum possible size of any of those arrows. All right, and then we get a sine kx minus omega t, and I believe this was in the k hat direction for this problem. So here, this is the electric field, and this would be the electric field amplitude. All right, now I want you to notice something. The electric field is oscillating in the up and down direction, the j hat. The magnetic field is oscillating into and out of the page, but the wave is propagating in the x direction. Notice it's kx minus omega t. That means in the x direction, opposite of this sign to the right. So we see this is we see a wave that's traveling to the right, but the oscillation of the electric field is out of the page. Up and down. The oscillation of the magnetic field is into and out of the page. The energy of a photon. Okay, so I haven't really mentioned what a photon is. We've talked about electromagnetic waves. We can also describe electromagnetic radiation in corpuscular form or particle form. So when we do that, we call it a photon. The energy associated with that is hc over lambda, or hf. If you're a chemistry student, sometimes you'll see it as h. I'm not good at writing this, nu. That's the Greek letter nu, where Planck's constant is this thing h. It's 6.626 times 10 to the minus 34th joule seconds. All right. Now, So if you have a photon and you want to know how much energy is in that photon, we could do this. We're going to come back to this over and over again. I'm just kind of giving you a crash course right now of some of these things that these are probably the most important things to see and talk about. I'll be honest with you, I tend to focus on these equations more in my Physics 163 class. Other teachers may differ. But we're going to hit this over and over again, especially when we get into modern physics. So for now, you can just kind of say, oh, that's neat. That's cool. There's some neat little letters and symbols. At the beginning of this chapter, we are going to focus more on, whoa, come on, this type of stuff over here. And we're going to go into detail. We'll talk about refraction, reflection, Snell's law. We're going to talk about polarizers. And so actually one of the first things we do is we'll talk about polarizers, and I'll just leave that for the next video. Is there anything else I should say here? If you look on page 3 of the workbook, there's a whole bunch of other stuff. Every instructor is a little bit different in what they want to cover. I tend to cover radiation pressure in an electricity and magnetism course, and so things like that. I will probably, I don't know, I guess maybe I should mention one more equation here while we've got it. I guess I'm assuming you know this, but in general for waves, V equals F lambda. So C equals F lambda in a vacuum. And we'd say V equals F lambda N in other medium. In another medium. Okay. So, right, you'd have remember that this here is C over N, and this here is lambda over N, and the over N's will cancel out. So you want to use wave speed equals frequency times wavelength. If you're in a medium, we have to use the speed in that medium and the wavelength in that medium. So just making sure you're aware of that. That's probably pretty important. We're going to hammer this in more videos. We'll probably pick up next with polarization. I think that's good enough for just a start.